Hi, I'm Johanna Michaels. I'm a journalist, and this is Anna Maria Hartkopf, who is a scientist and the head of MEP Labor, a fellowship program, which helped me realize my project. So yeah, today we want to take you on a journey through the geometry of space. So let's start with the video. Wait, maybe.
Sorry. Oh, no, it was actually right.
Okay.
No.
Finally awake. Good. I've been waiting for you to open your eyes because I want to show you something. Take a look around. Do you notice anything? No, I don't mean the curious triangles and squares here. I mean space itself. How would you describe it? It's
Sorry. Yeah, and I want to ask you the same question. How would you describe the space around you? Yeah, here are some suggestions. So there are 3 directions. You can go up and down, left and right, and front and back. And these 3 dimensions are perpendicular to each other. So they kind of build up a straight box around you, like a container in which we can move and orientate ourselves. So if you agree so far, you're on the same page with an ancient Greek mathematician called Euclid. Because our intuitive image of space is pretty much a 3-dimensional Euclidean space. So what is a Euclidean space? More than 2000 years ago, the mathematician Euclid came up with a theory of geometry. And what's unique about the Euclidean space is that it's flat. So there's no curvature in any direction, just like the box we just built in our mind. That means that in a Euclidean space, you can draw 2 lines right next to each other and they will never intersect, what we call parallels. And this is due to a postulate which Euclid formulated, the so-called parallel postulate. And it's valid in Euclidean space. And it says, in a plane, given a line and a point not on it, at most 1 parallel to the given line can be drawn through the point. Okay, so yeah, let's get some history here. Because how come that our intuitive image of space resembles some theoretical space some ancient Greek mathematician came up with more than 2000 years ago? Well, Euclid actually took the spatial knowledge of his time, systematized it, and made it the theory of geometry. So it's no coincidence that the 2 images resemble, since he based his theory on the human perception of space. But this is actually no one-way road, because Euclidean geometry is very present in our Western culture. We learn about it at school, and often it's the only geometry we get to know. So as much as Euclid influenced the human perception, was influenced by the human perception, he influenced our perception too. Yeah, so take, for example, take Newton's mechanics, where Isaac Newton took Euclidean geometry and formulated his equations of motion, which only work in the Euclidean space. And he didn't even motivate this. So he just presupposed Euclidean space without even arguing for it. So that's one example how we're kind of shaped by Euclidean geometry in our thinking of space. Okay. Oh, sorry. So, okay. So now we know where our intuitive image came from. But does this intuitive image describe space correctly? Because after all, we know that our intuition can be awfully wrong, especially when it comes to modern science, or in this case, modern physics, which deals with the description of space. For example, Albert Einstein and his theories of relativity pretty much left intuitive grounds completely. So according to the special theory of relativity, space is now entangled with time. And this new concept of space-time doesn't work in Euclidean space anymore, since according to the general theory of relativity, gravity is nothing but curved space-time. So when you take the Earth, which circles around the sun, this is because the sun shapes and curves space-time around itself and makes it kind of a bowl where the Earth is circling around. So it seems like our intuition is of no use when it comes to describing physical space. But is there a way to change that? Is there a way we can get science and intuition back together? Yeah, that was the leading question of my project that I realized together with the MEP Labor, and where users can experience non-Euclidean geometries. So back in the end of the 19th century, when every physicist was convinced that space is flat, just like us, we had this intuition, just like Newton did. Einstein could only overcome these intuitions, these implicit intuitions that in the end we now know that they're inaccurate. So we came up with a VR journey where yeah, we want to invite people to do the same as Einstein, to question their everyday beliefs and see what's possible. So we had two goals. First, we wanted to make these strange laws of Einstein's complicated theories a little more accessible to non-scientists through the VR journey, where they can experience what non-Euclidean geometries are like. And second, we wanted the users to learn a skill that is very important for every scientist, which is to reconsider what they implicitly took for granted. Okay, and now Anna is going to tell you a little more about the MEP Labor.
Yeah, thank you very much. Yeah, I just want to tell you what the project behind the project is, because Johanna was just telling you about her VR project. And in the MEP Labor, the MEMP, it stands for Mathematics, Computer Science, which is Informatik in German. So that's the I, and P is physics. So that's a research project for science journalism. And we are giving out fellowships to journalists who want to dive deeply into an MEP related topic and develop an innovative media format. And this is what Johanna did with the VR journey. And we even brought VR glasses. You can try it out later if you want to. And then you can try. We show you a video, but yeah, for the real experience, we brought this thing. Yeah, so what is the MEP Labor is, as I said, for journalists who can come and have a fellowship and do something similar to what Johanna has been doing. And also it's very important for the for science and the dialogue between science and society. So we see ourselves like in science journalism as a part of science communication, and we want to build trust with society via quality journalism. And yeah, then on the other side of that is the society that can engage in a dialogue about the topics, because some of those topics are sometimes a bit perceived out of reach. Yeah, and then the media also profits from it, because after our fellows did a half a year or 1 year fellowship with us, then they are experts on topics that relate to mathematics, computer science, and physics. Yeah, we need more people who can do that. Yeah, that was just a little bit of info on how the the project actually came to be. And now we want to show you, what does it look like, the non-Euclidean space? And here's a little cutout from the experience.
Well, I wanted to show you something. The Euclidean space is not the only one there is. If you take a bite of that fruit over there, I'll show you a space that would have knocked old Euclid out of his sandals. Do you dare? Then focus on it. Did I promise too much? This is what space looks like when it's no longer flat, but positively curved like a sphere. That's why it is called spherical space. Here there are no parallels anymore. There's a rule for all straight lines. They always meet the lines of.
Okay, that was the end of the video. What you can actually experience, what you can experience when you're in this spherical space, like really fancy things happening. But if something, normally an object, when it gets like further away, it gets smaller, but then it actually gets bigger. And that's a surprising thing to see. Okay, I think that's that was it from our side. Thank you very much for listening. And if you have any questions, we're happy to answer.